Okay, so the last topic that I have to teach is the topic about the QR method. So the QR method has to be done, can be used after we have a tridiagonal matrix. So QR must be used, in this case, it can be used after the householder's method. There are many methods that can be used to do tridiagonal metrics, but I'm just going to talk about one topic, which is the householder. And now let's just go to the QR. So after householder, we have a matrix that looks like that. So A1, A2 up until AN on the diagonal line, and then I'm just gonna call B1, B2 up until Bn minus 1, B1, B2 up until Bn minus 1 on the off diagonal line. So the A's and the B's are the location in which you are allowed to have non-zero entries. Otherwise, the remaining spots are the zeros. And then the idea of the QR is that we want to split A into Q times R. In this case, the R is actually an upper triangular matrix. Upper triangular matrix. And Q is an orthogonal matrix. Okay, so with the specific qualification of Q and R, then you can have, pretty much achieve the eigenvalues. Our upper triangular is like this. I think you guys should remember. So these are all zero. These are okay to be not zero. Okay. If you split A into Q times R, the next A, the A in the next iteration is going to be R times Q. Note that, the order is different. So when you split A into Q times R, the next one you just switch the order and make it R times Q. And then if you keep doing it, eventually you can get an eigenvalue. And if you keep doing it, eventually using the QR method, eigenvalues can be achieved. Okay, so let's just prove a little bit. So let's see a little bit of the proof here. You say that if you split A in the kth iteration to be Q times R, multiply both sides by Q inverse, we're gonna get Q inverse AK equals to Q inverse QR. So Q inverse Q is just I, so you just get the R. So basically your R is just Q inverse AK, right? Or since Q is an orthogonal matrix, Q inverse is just the Q transpose and then times AK. Let's just keep this equation. So now the next AK plus 1 equals to R times Q, as we said earlier. And we say that R is just Q transpose A, so Q transpose AK times Q. Since Q is orthogonal, then multiply AK with Q transpose and Q makes AK plus 1 having the same eigenvalues as AK. So, you can do it many times, and this is going to guarantee that your AK plus 1 is still going to have the same eigenvalue as the AK. And this is why the method works. So now the only question is, how do we construct Q and R? So in order to construct Q and R, we need a matrix P. The metric P here, starting with the P2, I don't know why they start with the P2 rather than a P1, but they started in the P2 in the textbook, so I'm just going to do P2. So for the 3 by T, for 3 by 3A, an example is like this. So P2 is going to be cos theta, psi theta, minus psi theta, and cos theta. Don't be intimidated by the trigonometry, right? Because I think this is nothing, you're not going to do cos psi anymore, but we just use it. Eventually, you're going to get a formula for it, okay? So actually, the P here is first it begins, so to construct P2, begin with an identity matrix. So you begin with an identity matrix, and then along the diagonal line, you can put cos, psi, minus psi, and cos there. Okay, let's see, for example, but first the P2, property of P2, actually P2 again is orthogonal. So when P2 is orthogonal, then again P2 equals P2 inverse equals P2 transpose. Let's see, for example, if you have a 3 by 3 matrix, 3, 1, 0, 1, 3, 1, 0, 1, 3, you have something like that. Step 1, by P2 times A. The purpose of the P2 though, we need to have a matrix P, right? P is gonna be used to construct R and Q. So let's see how we do it. So P2 times A, P2 we said earlier that it's the cos, psi, minus psi, and cos. 0, 0, 0, 0, 1 times A, 3, 1, 0, 1, 3, 1, 0, 1, 3. You multiply the two matrices, and this is what you get. You get 3 cosine theta plus sine theta minus 3 sine theta plus cosine theta. Cosine theta plus 3 sine theta, and then minus sine theta plus 3 cosine theta. This is 0, 1, 3 sine theta cosine theta. So the first multiplication, our aim though is to make, so the first multiplication here, we want to make the first column of this multiplication, make the first column of this multiplication be like an upper triangular matrix. So if you want something like this, that means, so no, you want this to be 0, you want to make it more like an upper triangular matrix. Other values, we don't really care. It can be anything. So what we want is we want minus 3 sine theta plus cosine theta to be 0. So if you just, move things around, you get tan theta equals to 1/3. So theta is just the arctan of 1/3. So once you know theta, you can know cosine theta is going to be 3 square root of 10 divided by 10, and sine theta is just square root of 10 divided by 10. So once you solve for the theta, you can know cosine theta and sine theta. So you plug this in, plug cosine theta and sine theta into P2A above. So we get P2A equals to square root of 10, 0, 0, 3 square root of 10 divided by 5, square root of 10 divided by 10, 4/5 square root of 10, 3/10 square root of 10, and 1 and 3. So, okay, the first round of it, it's not really like this is in just the first, the very beginning, we find P2, and then once we find P2, we multiply P2 with the A, this is what we get. So next, find the next P, find the next P, we call P3. So for P3, the property is going to be pretty much the same, which is starting with the identity matrix, but you just move the cos theta, sine theta, minus sine theta, and cos theta down along the diagonal line. So once you have P3, then P3 times P2 times A, this is going to be, 1, 0, 0, 0, 0, cos theta, sine theta, minus sine theta, and cos theta times P2A, which is what we just got, square root of 10, 0, 0, 3 square root of 10 divided by 5, 4/5 root 10, 1, 3, 3/10 root 10, and finally 1/10 root 10. So you multiply things up. So you multiply things up. Let's see. In the first column, you have square root of 10, 0, 0, right? And then in the second column, you pretty much have 3 square root of 10 divided by 5, 1 square root of 10 divided by 10, and then later on you have 4/5 root 10 cosine theta plus sine theta, 4/5 root 10 minus sine theta plus cosine theta. So in here, you get 310 root 10 cosine theta plus 3 sine theta, and then 310 root 10 minus sine theta plus 3 cosine theta. So what you want again is that you want this to be equals to 0. Okay, so in order to have this to be equals to 0, you get, 4 minus 4/5 root 10 sine theta plus cosine theta. So for theta, and then 5 cosine theta and sine theta. Then plug in cosine theta and sine theta up back to the above matrix, and then finally you get P2 times P3 times P2 times A. This is your final product, which is going to be root 10, 0, 0, 3/5 root 10, 2.720, root 10 over 10, 1.985, and then 2.44. So as you can see, this is of the form upper triangular. So basically, this is your R matrix. Okay, hence R equals to, this is P3. P3 times P2 times A. And from previously, you know that R equals to Q transpose A. So you can see that P3 times P2 is just the Q transpose. Hence, Q transpose is just P3 times P2. That means Q is just P3 times P2 transpose, which is going to be P2 transpose times P3 transpose. Okay, so I have to put this into a box here. So the only problem is that how do we find the P, right? Do we have to like do the cos and the sine and solve for theta every time that we want to solve for the P? The answer is no. It's really easy to find the P. So let's just use the formula. First, to construct a P, okay? For the 3/3, you already know about it. Let's just see, for example, 4/4. Then you're gonna start with P2. Your P2 will be something like that. Cos sine minus sine cos 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0. So this is P2. P3 is going to move along the diagonal line by 1 unit. So this is cos sine minus sine and cos 0, 0, 0, 0, 1. And finally, your P4 is just gonna move one more step further. So this is 1, 0, 0, 0, 0, and your cos sine minus sine cos is moved here. Okay, so this is how you construct the P, and then to calculate each cos and sine, then assume A equals to A1, oops, A1, A2, A3, A4, B1, B2, B3, B1, B2, B3, 0, 0, 0, 0, 0, 0. Assume that you have a 4x4 tridiagonal matrix. Then for P2, the location of the cos psi minus psi cos is just in this box. So you're gonna just care about these two values. So for P2, the cos is going to be just A1 divided by the square root of A1 square plus B1 square. And the psi is going to be not A2. B1 divided by the square root of A1 square plus B1 square. So this is for P2, right? For P3, then your A is going to change. Your A is going to be something like that. So you're going to have, whatever values here. And these are going to be all 0. Okay. And now you have something like UVWZ. So these are going to be the values that you have for the new A, right? After multiply with P2, this is what you have. So for P3, your cos theta is going to, since your P3, the location of the cos and psi are in this box. So your cos theta is going to be U divided by square root of U square plus W square. And your psi is going to be W divided by square root of U square plus W square, okay? And again, for P4, your A is gonna change to be in another format, which is gonna be any number here, 0, 0, 0, any number here, 0, 0. So whatever values here, so let's say A, B, C, D. So if you have these 4 values here, so this A is just P3 times P2 times A. So after you multiply A with P2 and P3, you want to solve for P4. Then for P4, the cos theta is going to be A divided by square root of A square plus C square. And psi theta is going to be C divided by square root of A square plus C square, and so on and so forth. Okay, so if you have like a 10 by 10, just keep on doing this. All right. So let's see in MATLAB, how do we implement this? I'm not gonna pause, and then I'm actually gonna just go forward into MATLAB and do it. I might do something wrong though. So if I do something wrong, I'm just gonna pause it and then continue back later on after I solve my problem. So let's do this. A is just after tridiagonal form. Let's just do this one example because I'm lazy now. Okay, let's just do this 3 1 0 1 3 1 and 0 1 3. So it's going to be 3 1 3 1 0 1 3 1 and 0 1 3. So you have the A, right? And then after you have the A, you want to construct the P. So in order to construct the P, you want to solve for the cos and the sine, right? So for solving cos, it's going to be A11 divided by square root of A11 squared plus A12 squared. Actually, 1, 2, or 2, 1 is going to be the same value, but I'm just going to say 2, 1 just to match my lecture. This is too long. I'm just going to calculate it outside of this calculation. So let's assume that my z is just square root of a11 square plus a21 square. So my cosine is just a11 divided by z. Sine is a21 divided by z, right? Sine and cosine. Okay, so P2, here my P2 formula is cosine is just this number divided by the square root of the square of the summation of the two number, and then sine is just this number divided by the square root of the summation of the square root. So it should be right. So once you have the cos and the sine, then C is like, this is cos theta. So this is cosine theta. So this is, S is a sine theta. Because I'm too lazy to type it in full. So now let's see. My P2 is just going to be I of 3. Actually, I don't want to use 3. Let's just do 3. Let's use. Let's find the size of the A first, so then I don't have to change it later on. Size A is N, so this is just going to be I of N. Okay, so then my P11 is just going to be cosine P12 cosine and then sine. P21 is gonna be my minus sine, and then P22 is gonna be my cosine. Okay, let me just pause here and save it first. So this is my QR SIC 450. All right, so I do my P now. Let's just check my P a little bit. So this is my P cos sine minus sine cos. So now if I multiply my P with the A, actually, I don't want to do anything with my original A. So let's just use the new name. So this is B, and then let's just say A equals to B. So I can use A later on, okay? So everything will be A. Now, my new A is gonna be P times A, okay? So if I multiply my P2, this is actually P2, but I don't wanna use P2, I wanna use the same P for all the P's, like the same name for all the P's that I use. So I can make a loop here. But before I make a loop, let me show you. After multiplying P2 with the A, this is what I have. So I have, 0 out the first column starting from row 2. So my next job is to find another P and multiply this in order to make an upper triangular matrix. So in order to do it, I just have to calculate everything else starting from here again. So let's just do it. All right. In the second round, I have to find my new cosine and sine. So this is going to be changed to 2, 2. So this is going to be changed to 3, 2. So this is cosine is going to be 2, 2. Sine is going to be 3, 2. P starting with the I's, and this is going to be 2, 2, 2, 3, 3, 2, and 3, 3. Okay, so after doing that, updating the A, I should get an upper triangular matrix, which is going to be my R actually. All right, so now my A is the R matrix. So once I have this, I want to calculate my Q2, so let's just begin with the starting Q. Let me start with the Q equal to an empty set. Starting with the Q of an empty set, then after I have my P, then maybe here I can say that my Q is just, so I have to, in order to calculate my Q, if we take a look in the slide, Q is just P2 transpose times PT transpose. So it's gonna be Q times P transpose. Note that, the reason that I put Q in the front here is because I want to use this in the next round. So I want to have the same pattern. Here, if I do like this, since this is the first time that we have, so we only have P2 transpose, and it's fine. But as mentioned earlier, I want to have the same pattern everywhere. So I'm just going to put Q here. Okay, so once I have my Q updated, next, my Q in the next round is going to be Q times P, right? The new P transpose. So once I have my new P, then I multiply my new P transpose with my Q. Then I run it. Oops, did I do something wrong? Inner matrix. Q equals to, oh, okay, sorry. I cannot do this because I have to say that Q is IN. So starting with an identity matrix, so then I am allowed, it's legal to multiply identity matrix Q here with the P. Otherwise, if I multiply an empty set with a 3 by 3, MATLAB will get error. So if I run it again, I should get the answer now. So this is my Q. Okay. And I think I did something wrong. So my Q has to be, okay. Starting with the Q as the identity matrix, then I multiply that with the P transpose. Then I can update my Q. Then after I get a new P, then I multiply P in the back to get P transpose to get the Q, right? So it should be correct. I'm not sure if I'm correct though. Let me just double check something. Let me just do, if my Q is correct, then I have to have Q times Q inverse of INV is the inverse of Q. If I times Q with the Q inverse, I should get an identity matrix, which is the correct one. So I think I did it correctly. So if I copy everything, starting from here, copy, and then I paste it. Or I don't want to do this anymore. Okay. This is the first round, and the second round, I want to just delete it. Okay. Let me run it again, I'm sorry. Okay, I'm running it again. And here, let me check A and Q. Okay, so now I have my A and my Q. I'm just gonna put a loop here. For, oops. I have to have Q equals to I every time that I do it, because otherwise my Q will keep adding up, and I don't want it. I want to reset my Q every time. So if I want to run this code for like 20 times, let's see, I equals to 1 to 20, and then E and D, and then I run it. Let's see my Q. Oh, and then after I have my Q, then update my A to be R times, that not to be A is the R, right? A times Q. So after I calculated my R and my Q, then what I have to do is that I have to update my A, right? As mentioned earlier here. If I split A into Q times R, then my next A is going to be R times Q. So in my MATLAB code, I calculated my next A to be R, which is A times Q. So now if I run this code several times, 20 times, then my final A looks like that. So if you take a look at that, 1.5858 is in the last row and the last column, and you can see that the number in the first two column here is 0 and 0, and the number here is also 0 and 0. Then if if you have the output that looks like that, in which all the other numbers in the same row and in the same column are 0, that number is actually the eigenvalue of the matrix. So we can get the first eigenvalue to be 1.5858. And once we have this first eigenvalue, then what we're gonna do is, let me just write this down so you guys might wanna try to understand it. Print screen, I hope that it worked. And let me just put it down here. Hopefully. Okay, good. So once you run this code for several times, this is gonna be the first eigenvalue that we get. Once we get this first eigenvalue, then if you can see that these are going to be all 0, then you can presume that this is the eigenvalue. Then what we're going to do is that we're going to have to do size reduction. So this matrix will be used as the new matrix and run the code again, just like we begin solving for the eigenvalue. Okay, so this means that, so let's say, for example, you have A, which is like a 5 by 5, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If you run the A and then eventually after the first time you run QR method, you get something that looks like that. 0, 0, 0, 0, 0, 0. So the first time that you run, this is going to be your eigenvalue. So if you get everything here to be 0, then this is your eigenvalue. And once you get the eigenvalue, the remaining 4 by 4 will be used as the new matrix and rerun QR code again. So we're gonna use the remaining 4 by 4 to do QR again. And after you do QR again, you're gonna get something that looks like that. So this is a 4 by 4. Now, your size will be reduced by 1. And again, you get some number here. So this is gonna be your second eigenvalue. And once you get the second eigenvalue, this 3 by 3 will be used, run QR code again, run QR again. Okay, and then once you run the QR again, your new A might look like that. So it's gonna be, ta-da, 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 ta-da. So this is your third eigenvalue. value. And again, you're gonna run this one again, run again. And this is the final time. Once you reach the 2 by 2, you just need to run it again until these two numbers are pretty much close to 0. So what we need is that we want these numbers to be close to 0. So we're gonna run it. In this example, I just assume that, you know, by running it 20 times, you can pretty much get these two numbers to be close to 0. So let's just see, what if I only run it for 2 times? What's gonna happen? So for I equals from 1 to 2, and I run it, then if you see my A, you can see that, you know, this is 0.5724, which is still large. So we don't want to stop now. We just want to keep going. So another way that we can do it is that we can check this number. If this number is small enough, then we can say that, oh, okay, we're gonna stop it. Otherwise, we're just gonna keep doing it. So maybe we can say, you know, tolerance is 10 to the minus 4, maybe. So if you have a tolerance, then you might want to say while TOL is less, while I don't want to see ERR, but I want to say this number. I can see ER. While the error term is greater than TOL, just keep going. Otherwise, just stop. And then here, at the very beginning, I want to say that my ERR is going to be A in the position 3, 2, right? Here, in the position 3, 2 is here. If my ERR, which is A in the position 3, 2 is small enough, then I can stop. Another thing that I want to modify my code is that, let me just run it for a minute. Oops, I did something wrong. I think I forgot to initialize my ERR. So ERR equals to 1, and I want to count to K equals to 0. Okay, and then I want to say K equals K plus 1. Okay. And I want to make it a bit more fancy, so N equals to 100. So ERR greater than that, and K is less than or equals to N, then just keep going. Okay, let's see my A, and let's see my K. So I've run the code 16 times. Okay, and then I have you know, two things that are repeated here. So I want to make it in a loop. So for I equals to 1 to 2, or N minus 1, then what I want to do is I want to put this in a loop, E and D, and so this I can just comment it. So this one I can comment it because it's the same thing. Alright, so then I can just update my I. So this is I plus 1, I. Okay, so this is I, and this is I plus 1, I. And this is gonna be I plus 1, I plus 1, I. And this is gonna be I plus 1 and I plus 1. Okay, so if I have this code, then pretty much I think I should be able to do it. Okay, run it. Alright, so again, my A is going to be like that, and I'm running the code 14 times. Note though that this QR is not finished yet. you still need to like do it. So after you get this, you might want to store your eigenvalue. So let's see, somewhere around here, you might want to say lambda is just an empty set. And then once you get the first eigenvalue, you might want to say lambda is just lambda. And then you put A33 as the first eigenvalue that you get. And once you have this, then you can say that your new A is just going to be A from 1 to 2, and then A from 1 to 2. Okay. And once you have your new A, then again, you have to rerun this code. So to rerun the code, I think you need to copy from here up until here, copy, and then paste it. Let me see if I have to fix anything. All right. Store my lambda, resize the matrix A. And once I have the matrix A resized, then initialize my new ER, initialize my new counting, n equals 100, doesn't have to change. So while ER is greater than tolerance and K is less than, do the equality. Okay, so my new N is just gonna be 2, right? So I need to know the size again. So N equal to size A. So my new N is just gonna be 2. Actually, I can use N here, right? So this is N minus 1. Okay, and this lambda is just gonna be N. I'll make it more. So N minus 1, N minus 1. Okay, and then update my N. Get a new N, do the new loop, do the new QR. Oh, I forgot so many things. I have to copy these two in the same loop. Okay, so once I have my A, my R, and my Q, phi A equals to R times Q, phi the ERR, and then update my K. So I run it again. Let's see my A. Did something wrong. A equals to. I think I do something wrong, right? Let's just see. Okay, A equals to 1 n minus 1 and then 1 to n minus 1. I did something wrong here. Run it again. And let's see my final A. So after reducing the matrix, this is my new A. Oh, so it's not correct. So for my new A, why is it not correct? So this is my new A, 1 to n minus 1. And then I update my N, ERR. For error term equal not is greater than the tolerance, K is less than or equals to N. Then I just keep running it. I from 1 to n minus 1, so I just do one round. Q, Z, A, I, cos and psi, P. This is my R and my Q. After I get my Q, A is R times Q. Update and let me just comment this for a minute and then run it. Okay. So this is my A after, oh, okay. See here, CLC, run it again. Let's see my A. I think my A is wrong since here. Let's see if I did anything wrong here. Okay, so after I did finish this, I store my lambda, then just comment this one, run it. And then let's see my A. Oh, I think, did I make a mistake in my code earlier? Hang on. Okay. Yeah, one greater than. Okay, let me just pause for a minute and then I'm just gonna fix it and then come back to tell you what